Welcome to our detailed metric walkthrough of Vertana AI Factory Observability. We'll begin by reviewing the overview dashboard, which summarizes the entire infrastructure, discovered programs, factories, hosts, and GPUs. Our platform collects data every minute for GPUs and GPU programs, and our reporting engine lets you filter, segment, and aggregate this data by hosts, factories, and applications. Today, we will use a single host to showcase the types of data available. All host and GPU entities feature individual views, which can be customized to showcase critical metrics. Let's walk through our GPU hosts views and cover data like configuration, energy, errors, network, NVLink, program information, storage, utilization, and topologies. The landing page for any entity is the overview. This customizable view highlights core entity properties, related components like GPUs and running programs, as well as overall health status. Configuration data is critical to understanding how a GPU communicates during scale-up or scale-out. We capture properties like brand, model, and serial number, alongside fundamental hardware details like NUMA and CPU affinity. We utilize the logical NVIDIA tree to identify relative component closeness. This determines the path type, which helps prioritize components for GPU processing. We also track PCI, sent, and received rates to monitor data transfer to and from main memory. These metrics are essential for correlating GPU slowdowns with memory bottlenecks, such as data copies across different NUMA nodes. GPUs can consume large amounts of power, leading to spikes, brownouts, and increased utility bills. The corresponding rise in power can also affect GPU temperature. To help keep tabs on energy, we track instantaneous power, total energy consumption, kilowatt hours, and temperature per GPU. Some power metrics are also tracked per program, allowing us to correlate how power and temperature affect GPU utilization and performance. Hardware failures are common due to intensive power requirements and temperature fluctuations. Therefore, we track hardware error counters like single bit, double bit, and PCI errors per GPU. These errors are aggregated across host and factory levels and serve as early indicators of potentially failing hardware. As the network expands, scale-out and storage access become critical. Our platform integrates with IP storage networks, using SNMP to map connections between IP switches like Cumulus and Sonic to hosts and storage arrays using MAC address tables. Combining this with configuration data, we can identify the likely paths GPUs will take when performing scale-out training or accessing storage. Beyond scale-out, we track scale-up connectivity via NVLink connections within the host, supporting direct GPU to GPU and GPU to NV switch setups. We track the bytes sent, bytes received, speed, and utilization for every NVLink connection. Our agent actively scrapes running PIDs on each GPU. We categorize processes by program name or environment variables to group similar PIDs into a single logical program entity. This allows us to track which PIDs are running on which GPU, down to a 5-second granularity. Programs are grouped to answer critical questions. What was running where? How long did it take? And what utilization did it consume? We can detect both historical and currently running programs. We use the detected IP storage network to access backing storage arrays. For supported arrays, we collect detailed insights such as disk latency, rebuilds, volumes, and queues. The goal is to ensure your GPUs are as utilized and efficient as possible. Therefore, we provide numerous utilization and efficiency metrics. By comparing advertised and current utilization, we calculate the percentage of GPU throttling. Throttling due to power temperature issues or idle GPUs is often desirable as it preserves hardware and reduces costs. However, throttling becomes an issue when it impacts running programs. Therefore, we track not just GPU throttling, but the percentage of time it impacts applications, in addition to overall GPU utilization and efficiency. We provide detailed breakdowns of various types of GPU utilization, including the graphics engine, tensor pipe, and floating point calculations. We also capture and show encoder and decoder usage and frame buffer memory. AI factories introduce new concepts, networks, and relationships between components. Our topology engine tracks numerous connections and renders different views to answer specific questions. For example, our topology answers which NIC is GPU2 likely to use for scale-out or which switches are involved in a scale-out operation to host B. Our engine is capable of defining focused topology views tailored to customer needs. We saw this in the program view when we observed the programs and which GPUs they ran on, and in the NVLink view in regards to the network scale-up and backing IP switches, and storage arrays in the network view. Thank you for viewing our Vertana AI Factory Observability detailed metric walkthrough.